Yeah, I want like I've been wanting really long hair for a while. But like I don't know, maybe.
All right, everyone. So today, I assume people would like to know the statistics on the exam. I haven't released the grades yet, but we do have all the grading done. We have for a little bit. I wanted to talk to you all about the grades before I release them, though, because I have a feeling that people, as students do, are going to freak out a little bit. But I want to talk about it a little bit ahead of time. Okay? So first off, you all felt the difficulty of the exam. It was not a tremendously difficult exam, but it was a difficult exam. It was harder than you might get in a lot of these classes. But the difference and where you will see like the average in class and all this comes from is that we graded more harshly. We graded more thoroughly, I'll say. That is both, we took off points for everything that was wrong on your answers, and also we gave very thorough personalized feedback. I went through every single one of the assignments. I gave at least 2 comment bubbles to, I'm pretty sure. So you will have very thorough feedback on this. Secondarily, I will remind you of the fact that I told you at the beginning of this class that the exams were going to be harder, they would have lower scores, but that your attendance was the scaling, okay? So I want to do a little math with you for you all to realize what that means. So if I have the exams weighted as much as the in-class attendance, then that means that what you could consider your exam grade to be, this is making up that difference, is halfway to 100 from what it is, okay? So if your grade was, say, a 60, it would actually be an 80 with that sort of innate scaling, okay? So just so you know, this is the pedagogy here and all of this before you all freak out. Give me 1 second to switch out this, and then I can show you the thing. Okay, calm down. Oh, that's the wrong one. There you go. So, okay. Ready? Okay. Give me. Okay. One moment. Everyone can react in just for like 5 seconds. Get out of your system. 3, 2, 1. Oh my God! It's a 66. Okay. So yes, the exam average is a 67. This is on the makeup. The main exam had an average of 64-ish. And they're pretty similar. I want to talk about where these points were lost and all of this stuff. You also see no one got 100, so you can also, for whatever you want to tell your friends later about how hard the exam is, no one got 100. So it seems like the majority of the points, so it's fairly evenly distributed where the points were lost. Most heavily were on the algorithm design and the algorithm analysis portion of the class. That's where we were, that's where you can get most of the things wrong. The multiple choice were around like 80% on average people got them, except for one of them, which we'll talk about that in a second. But overall, it was mostly lost on those parts. It's mostly because those have a lot of things you can do wrong. They were hard problems that had multi-layers of difficulty. You might have realized one part of it, but not realized the next part of it. Anyway, so you can also look through each one of these, and you can see what the average score was for each one of the questions. 4%. That one, it did surprise me how few of you got. It's a hard problem. It was the tricky one of the multiple choice. It surprised me how many people got it wrong, but it is a hard problem. The TAs got it wrong, by the way. I asked them it too, and they also got it wrong. I promise I'm right, though. Anyway, so these were the exam scores. Fairly high standard deviation, higher than I would like, but not tremendously. Mean is kind of about what I wanted, actually. I know that sounds brutal, but this is about what I expected from it. Again, if we consider that this is weighted equally or less than our attendance, then we can take this and then we can average it with 100, assuming that you're attending class, which I think the people attending class today are. Then you can see that this is about at 85. 85% is sort of adjusted for inflation, if you will, or deflation, I guess, is what the average score in the class is, which is about what I wanted. Okay? Now, I want to remind you all also that these numbers are kind of make-believe. The point of them is to tell you how you're doing in the class and also giving some sort of comparison between students, and so that I can make a judgment call of how much you know and where the cutoff should be for A, B, and C and stuff. So just try to not let the number get to you, and I'll tell you this is about what I wanted on the exam. This is about what I expected, about what I wanted. Just take a look at the feedback. I can promise you every single person got something wrong, so all of you have something to look at in the feedback. We also will leave regrade requests open for about a week. If we leave it more than that, then someone's just going to keep doing it. So it'll be 1 week. Don't be mean to the graders. We took basically our break spending. I spent about 8 to 10 hours grading, and I only did one of the questions. So yeah, I mean, I did the multiple choice too. So I guess if you think I graded that wrong, you're welcome to talk to me. Yeah, so it takes about 8 to 10 hours to go through and answer it the way we did. So try to not be mean to the TAs. It's possible that we have an oversight or something like that, and you can talk to us about the grading if you have some questions about it. But don't be mean to them. A lot of people, whenever people get low grades, we do get some people who are going to be aggressive about it. Just please don't do that. We will be reasonable. I promise you. We're very reasonable. Okay? Cool. Any questions on this? Yeah. So it was a different multiple choice. The exams were totally different. It was that this multiple choice people did better on than I expected. For the people who took the regular exam, this was a recurrence that included a square root of n. It ended up being an easy problem, but it was a scary looking problem. But a lot of people in the makeup realized how to do the problem, so it wasn't a big issue. I expected this to be lower, actually, so this is more of the surprise than the other one. This one, for anyone who took the makeup or wants to know, doesn't remember, was a question that asked how many comparisons are necessary to find both the max and the min of an array. I'll talk about it very briefly just because I'm sure some people are curious now that they got such a low score on this. The basic idea of how you can do this, the key to the problem is that you're finding both. If I found them individually, it would take more work than finding them simultaneously. So if I were to find the max, so if I had let's say that I have 4 elements, just to make it really easy to draw. If I have these, if I want to find the max, I can compare these two, and compare these two, and then I can compare whichever was larger out of these two, and that would give me my max. Okay? But the secret is that if I want to find the min also, then let's say that this is the larger, this is the smaller, this is the larger, this is the smaller, let's say. Then I know from this first round of comparisons, none of the ones that were larger are going to be the minimum. So in fact, I only need to do this comparison. Does that make sense? So that's the secret of where we can get some advantage here. Okay, so you think like splitting them into the larger half and the smaller half takes n over 2 minus 1, and then, or just n over 2, and then splitting them, once I have those half sides, each take n over 2 minus 1. So the answer is 3n over 2 minus 1. Okay? You can look at it again if you'd like. Not very many people got it. This idea, by the way, of reusing computation that we've previously done is going to be the focus between midterm 1 and midterm 2. That's going to be the focus of the material. So conceptually, like this idea of I can reuse computation I've already done, get that in your brain somewhere. We'll be talking about it starting on Wednesday, and it'll be a core concept. Today we're going to be talking about greedy algorithms, which is sort of a sub-primer topic to talk about all of that. One other thing about the exam. So there's a bit of drama, I suppose. So I put, as I announced on Piazza, I put a trap on the exam, and I think I can take this off now, unless anyone has any questions on any of this before we keep going. Okay, cool. Cool. If you want to talk about the exam, by the way, you're welcome to message me or anything. So, as people saw, I put a trap on the exam. I guess it's a little bit loud, but I'll keep talking. This was intended, it's one of those things where I had a very clever idea, and then once I had that idea, it was very hard to not do it. I also have been finding that cheating is becoming more and more of an issue in the class, and in things like this where I have the grades are sort of dependent on other people's grades. I really don't want people cheating to throw off the whole balance of the class. So I was trying to go harder on it this time. People had their complaints, which is more than fine. This is my first time trying something like this. I will say, by the way, that I 100% believe that the way I went about it ended up being totally fair. There are people who did get caught, and things are happening to them. I don't need to talk about that too much, but I 100% know that no one who was innocent got punished in any way. Additionally, by the way, the comments about the retest being unfair, which I got by the way, got a lot of messages from you lot, so cool. Guess I won't try anything. I got called by the dean too. You guys, yeah, fun. Anyway, the retest ended up I didn't actually do the retest where it affected anyone's grade, so no one who was innocent had anything happen to them. It was essentially just a check to see if stories added up, if it made sense, and there were additional traps on the exam that I won't reveal, maybe they'll be on the next one. That was basically just double checking those. That's what the retesting was, and part of it was I needed to make the retest sound scary. So sorry about the misleading and the stress for anyone who got accused, but the whole thing ended up being, I think, very fair. And only people that I'm certain should be punished are being punished. Okay? Cool. Any questions on it? Any complaints, by the way? You're welcome to tell me that this was a stupid idea or whatever. More than welcome. Should have put Boston in it. Stupid. Yeah?
Just give a hint as to where the other traps might have been.
Look at the difficulty of the bonus problems. Cool. Yeah. Anyone else? Yeah.
How many people actually got it correct?
How many people got it correct? Same number as put the trap answer, by the way. It was 1/9 of the class, so 10 people. 10 people got the right bonus and 10 people got the wrong bonus. Yeah. I was pretty pleased that people got it. There were a couple of pretty tricky questions in the bonus. A couple easy ones, but a couple very difficult ones. So I'm happy that people got it. Cool. Any other questions about that or any other comments? You all were pretty loud when it was anonymous, so you're welcome. You're welcome to talk to me non-anonymous. Yeah. I can do it literally right now. Maybe I'll do it while you guys are taking. No, I won't do it during class because then all of you are going to get distracted. I'll do it right after class. I promise it really isn't that bad. I know that they look scary and all of that. I guess I'll make one proposal, I suppose, too. So because no one got 100 on the exam, I am open to the idea of increasing everyone's score such that the highest scoring person gets 100. I poured 10 hours into finding who's cheating to help you all you guys. I say, I'm going to give you some meaningless points. Cheaters. Alright, whatever. So truthfully, it will not affect anything, really. In fact, the only thing that it would functionally do is that it would give a small bonus to the people who took the makeup. Functionally, because I'm increasing everyone's grade. But it does make the number look better, and at the end of the day, I mean, it is probably a more honest portrayal of your skill level in the class, I suppose. But I don't know, will you guys all do the survey, the course survey?
Yes.
I'll do this. Again, it does not affect your final grade really at all, but if you want the number to go up, I can make the number go up. Yeah. Thanks. Anyway, by the way, there is still, I've not revealed yet whether the midterms are worth, or the exams are worth 20 or 30%. I think I'll tell you all now that the reason I am debating between the two of them is I'm deciding whether or not to take the maximum out of your two midterms as your midterm grade. So another bit of a give me to you, all of you, of if you did very poorly on the first exam, now you know what the exams are like, now you know how they're going to be graded, and maybe now you know how much you need to study or how much you should attend office hours. Cool? Cool? All right. That one is TBD, but is, to be honest, that's pretty likely for me. I tend to be nice if I can help it. Yeah, but if you all promise to do the survey, then sure, maybe I'll do that. But I'll talk to you about it more in the future. Anyway. So that's all the administrative stuff. Any other questions? Yes?
How do you think the second midterm
way harder. I don't know. I think probably the concepts tend to be harder for other students, for most students. So we're talking about dynamic programming. If you want to know the thing to study for the next month, by the way, dynamic programming. That is, look up that term, find examples, whatever. That is the thing that you should study up if you want to do well in midterm 2. We're going to cover other stuff, but that is going to be the core topic. And there's a lot to talk about there. I'd expect it to be similarly difficult. I mean, the midterms were about the same difficulty, the makeup and the regular, and that's how I write my exams. So like that's roughly the difficulty you should expect. I don't expect it to be particularly harder, but maybe it'll be a touch harder. Yeah.
Are you gonna
I am not gonna say. I will say, if I were to put some other trap, perhaps, I would probably do a better job of it. Anyway, you have a question too?
Yeah, I have a suggestion. Instead of counting one of the midterms to get 20%, how about you count 2 of the exams out of the 3 to get 20%?
See, but I want you all to take the final. To let's go back to your question. The final will be harder. Okay, so everybody. If I'm giving you the max of the other 2, then certainly it should be harder. I mean, the final I want to be like a real test of your skill. I want it to be possible for someone to get an A in the class and get a 50 on the final, if you know what I mean. Like, I want it to be a real test, and I want it to be like, you know, it's possible to get 100, but you have to be really on it to get 100. It shouldn't be a gimme. That's it. I don't expect people who are getting A's to get a 50 on the final, but like that's just possible. You know what I mean? And also from the grading standpoint, it's at most 10% of your final grade, the final exam. So even if you got a 50, you lose 5 points final. Get some bonuses. You can make that up. Yeah.
Would you suggest we start?
No.
That's a telling point.
No. So leak code is a weird thing. I mean, it's not a bad thing for studying and practice if you want to do it. Don't become leak coders though. Don't become people who just do that as your whole thing. I recommend against it because it's becoming increasingly that the skill set that you need is in the proving, is in the designing, is in all of this stuff, not in the coding. And I would wager a lot of startups and stuff are now no longer doing coding interviews at all. And there is a certain value in doing leak code problems if you are sitting down and doing design and doing analysis and all that, but you probably aren't. You're probably just like, oh, here's an idea, code. Oh, it's not good enough. I'm going to look up the answer online, copy paste. Oh, I did great. And that's like, that's not really good. Not a good exercise. I'd say, do the bonuses in the class if you want extra practice. Do leak code if you want to. It's fine. I don't think it's bad. It's certainly good to do that rather than doing nothing. But don't think of that as like a saving grace. That's more just like a thing to do. I'm going to give you weird, hard questions, and you're not going to find them on leak code. Yeah, for the most part. The 2 colorable one you could get on leak code, actually. But there won't be any more of those, probably. Okay. Any last questions before we go to content? Okay. Cool. All right, so today we're going to start with a simple problem for you. It's going to be a sort of perhaps a trivial example, but I do want to talk about it. So I want you all to imagine that you are a thief, okay? And hopefully you don't have to use your imagination. And you're in a museum. And you brought a bag, a knapsack, and you know that it can fit some number of paintings, okay? But you don't know how many. So you go into the museum and you want to grab some paintings and add them to your knapsack and get out of here, but you don't know how many you're going to be able to add. But you also are an art genius, I suppose, and you know the value of every single one of the paintings. So the question to you all is, how should you approach taking the paintings if you want the most value possible? Give everyone a second to think. Hey, So, someone not in the front. You guys answer too many questions. Yeah.
I just have a question.
Yeah.
Is the like?
No, they're all the same size. Yeah, we will talk about that in a bit. Yeah, but they all are the same amount of size. So I can fit T paintings, let's say, in my bag, and I don't know what T is ahead of time, but as I grab paintings, once I can't fit one, I can go, oh, it doesn't fit anymore, I have to leave. Okay, so what do I need to do? What's my strategy? Sure, far back. What?
You know the value of
Yes, we know the value of every painting. Exactly. We will just take the maximum value paintings until we can't anymore. So I'd find the most valuable, I'd put it in my bag, then I would look for the next most valuable, put it in my bag, and I would keep doing that until I couldn't put it in my bag. Okay? This is, as I said, a trivially easy problem. In case you're curious, by the way, the knapsack problem is a more general problem. This is called fractional knapsack, or is equivalent to fractional knapsack, if you want to look up this particular thing. And it has a trivially easy solution. All I need to do is find the maximum and repeatedly add it. Now, this setup is the most simple version of what we call a greedy algorithm. Okay? So a greedy algorithm is a problem where we only look at local information, not global. I know maximization is sort of global, but we just look at some small case. We just say, find the largest painting, we take the largest painting, and that's it. I don't need to consider, does there exist some other combination that will be more valuable or fit into here? I just need to say, it's always better for me to take the largest painting. Okay? Now, does anyone have any proof of this? So it's very simple to describe, very easy, but how do we go about proving something like this? Yeah, Amanda? Yeah, no, that's exactly correct. So the general way to go about proving a greedy algorithm, there's a couple frameworks to talk about them. The basic idea is we want to show that the decision we choose will lead to an optimal subproblem. That is, if I have at any point, let's say I have n slots left. Oh, I didn't bring a good marker. No. One sec. I want to see if I have a better black marker. Oh, I don't. Oh, that's a shame. Okay, well, we might be, let's try out the other colors. Let's see. So the setup to it is that at any given time, right, we will have, let's say, n slots left, okay? We have n slots left, and we will currently have some, like, let's say, I'll use V for value. So we have some current number of slots open, and we have some amount of value. Right? And we show that the simple thing we can do, one simple thing we can do is we can look at this and we can say, okay, if I choose the largest value painting, the most valuable painting that is currently available, then I will have n minus 1 open slots, and I will have V plus whatever the maximum choice was. Okay? Now, what do all of the other options lead to? So all the other options would lead to a situation where I still have n minus 1 options, but I have something that is I'll have something that is less than or equal to V plus V max. Okay? And the insight here, I know this seems like obvious, and this is a very trivial example. We'll talk about harder examples very shortly. But in this, the main thing to see is basically I now have a subproblem that is n minus 1 size, and I have all of the same options, right? Except this one now has higher value. So what we can see, this is sometimes called greedy stays ahead, is one way to think of it, is we can show that every iteration, the greedy algorithm will always be ahead. That is, it will have all of the same flexibility as the other options, but will have a higher optimization score, in this case, value. Does that make sense? Okay, yeah.
What is the n stand?
N is the number of paintings I can still fit. So I'm saying at any given moment in my algorithm, I have n paintings I can still fit, n knapsack size, let's say, and I have a current value of V. So I'm just saying I'm looking at some snapshot in time of my algorithm, some arbitrary snapshot in time, and I'm saying if I were to choose the maximum choice, I will necessarily have equal to or more value with the same flexibility as the other options. Does that make sense? So this is the idea of greedy stays ahead, yeah? So a greedy algorithm, yeah, so what's, the only very formal, very nice definition is really difficult to explain, actually, which is a shame. the thing that really quantifies what is greedy algorithm, the intuitive answer is that it's any algorithm where we're only using some sort of local information, where we're making a decision at the moment that doesn't need to consider the future, right? So I'm choosing this painting because it's the maximum, and I don't need to think about, in the future, will I have the right options later? I don't need to consider any of those in my decision to make this. I just need to look at this painting and say, I will take it because it is the maximum. In a proper formulation of this algorithm, by the way, we would need to say that the paintings are already sorted, so I don't need to sort them to find the max. But that's a nitpick. That's a very small detail. I guess I'll give you a little bit of this, which is the way that we can actually formally define what is solvable by a greedy algorithm is through a concept called matroids. So this is not going to be tested in this class whatsoever. This is not something you need to write down unless you want to look it up later. But a matroid is sort of a schematic for certain problems, and if certain conditions are met inside that schematic, then that problem is considered a matroid. And matroid problems are all solvable by a greedy algorithm. This is a little bit of a little taste of algorithms theory. This would be like taught in like the 600 level algorithms class, for example. That's where I learned it, in fact. It's an interesting thing, but it's not particularly useful because it's hard to phrase something as a matroid, and it's usually pretty easy to see if it is a greedy algorithm. So not particularly useful, but that is a proper formal definition, is that it is a matroid, which is not super helpful. But usually you can see that like an algorithm is greedy if it doesn't consider full full information, and it just makes a local decision. In fact, how about what algorithm have we learned that would be a greedy algorithm? Anyone got any examples? I'll let people think for a second, but I'll call on you after. You seem enthusiastic back there, though. Do you want to? Prims? Okay, yeah. So prims is a pretty prime example of this, actually, because you think about when we're running prims, as a reminder, just in case anyone forgot what prims is. Prims is the one where we start with it's the MST algorithm. I'll do it over here so that I don't get in the way of the other stuff. The MST algorithm where we will select some starting node, and then we'll look at all the edges from it and just choose the minimum weight one and add it to our MST, and then we repeatedly do that. So you'll notice it does not consider global information. It only considers the local neighbors, and it just iteratively chooses the minimum weight one. Yeah?
What are you saying, though, that like crystals is still a greedy algorithm?
That is a good question. It is if it's very similar to this. It would be if the edges are already sorted. Which is a slight definitional thing. It basically is in short, but this is more obviously a greedy algorithm. Yeah. So the answer is yes, but also this is a prime example of it. Yeah.
Why is it necessary?
That is we're getting into Matroid territory. Basically, because we're saying it does not need to ever consider global information, and to sort something requires global information. This is a nitpicky thing that, like, if you're trying to say something is greedy and that's the one thing that's not greedy about it, you just say, okay, I sort it and then I run my greedy algorithm. Yeah.
So is it the same matter for the paintings?
Well, yes, exactly. Same exact thing for the paintings. We have to sort them first, technically, or we have to assume that they're sorted. If you look in a textbook, they'll make that clarification. Like CLRS, it says, oh, they have to be sorted, whatever they say instead of paintings. But it's not an important detail. It is important to remember in runtime, though, that we need to sort if we're going to do something like this. So good thing to keep in mind. But in terms of like defining what is and isn't greedy, honestly not that important. It's more important the idea that the only reason we talk about greedy is two reasons. One is because it's a good sort of framework for deciding how you could approach a problem. I can say, oh, this looks like something where I only need to use local information. I can just write a greedy algorithm. I can just repeatedly find the optimal choice over and over and over again, and I solve the problem. Second reason is because there's a lot of problems that greedy can't solve, and this will be a good compare and contrast to our more interesting topic, dynamic programming. I'm not saying that greedy is useless. There's plenty of real-life applications where you can use them, but we'll talk about those a little bit more later, actually. Today I just want to introduce you what greedy algorithms are, the types of problems you might expect to see that are solvable by greedy, and all of that. So, any questions on that before I continue? Yeah. So it's in comparison to any other possible way of making your decision. So in the case of this, I'm saying I make some other arbitrary decision where I'm not choosing Vmax, and I know that that value must be less than or equal to Vmax, because by definition, Vmax is the maximum. So it's just saying whatever it is, some arbitrary other decision, then I'm going to be less than that. So it stays ahead of everything else. That's how we say that it's optimal. Cool? This, by the way, you may notice, is kind of induction. So under it's called greedy stays ahead, and it'll be called that in some different literature you might find, but this is basically just a specific application of induction. And the other possible way, or the other rudimentary way that you can, or routine way that you can prove a greedy algorithm correct is exactly what Amanda said, which is showing that if I were to make any different decision, then I would have a worse score. And this has a lot of the same flavor, but it's essentially the same type of proof, but with a contradiction. So as before, the main ways that we're going to prove anything are going to be through induction and contradiction. But for conceptual help, you can think of the induction with greedy, thinking of proving that greedy stays ahead. It always has a better sub-problem than the other algorithms. And you can think of the contradiction case as being, here is a swap case. If I swap two different choices, then I would decrease my score. And it's a very similar type of proof, but essentially it's just a contradiction. We show that if I made a different decision, I would have a lower score. Okay? And part of the way that we're going to go about proving this, actually, I'll talk about it a little bit. The way that one of these proofs would end up functioning is we can say, imagine I have, I guess, I'll hold off on it. I'll hold off on it actually, because any questions before I say the next line? We got a quiz. I know you all missed them. I know you missed them. Here we go. I'm going to let you all give a go at proving correctness before I talk about it anymore. Come grab them. Yeah. Do you will. You can split up the stack to do it a little bit more efficiently. There's one more? I printed out 90 of them, so there's enough.
I split the stack initially. Oh, right. No, I tossed those stuff around my way.
Who has a stack of exams, or of quizzes? Is it right here? It's back there. Here, can you split it? Okay. Go find the exams. Go. Find them.
I just put it there.
Yeah. If there really aren't enough, by the way, then just sit with someone and work with them. It's fine. But try it on your own if you can.
What? Oh, Dr. I can ask him. Dude, low-key, like, I don't even drink free living. I remember, like, last semester. So, like, for a grad course, I can hear that.
What?
Like,
I'll
ask again.
That's really weird. Just sit with someone if you don't have it. Maybe take a picture of it and then work on it. Yeah, I'm surprised. I printed out 90 of them. I swear. Right. Yeah, just take a picture of someone else's. It should be fine. Yeah. Okay.
Okay, cool.
Again, the technical details of the suing. So it's not really cheating. If you want to say, I store my stuff and then I run this grading algorithm, that's fine. No one's going to find that.
Am I allowed to say, well, my group does finds like.
You can also say that, you can say it, it's fine. You need to account for it in your runtime.
Right.
But in terms of, if I'm going to say like, oh, that's not a greedy algorithm, I'm not going to.
No, I know, I'm just saying, like, if I were to assume a data set sorted by state relation.
Yeah, you can do that. It's fine. I got a lot of it. Anyone need one? Sure. This feels very watching.
I thought that was really stuck away.
And then if I can't do better, then I
Learning out how to do it is the doing it part. Alright, you can talk to neighbors now. You can talk to neighbors now. Discuss.
it's like it's the
I don't know, I guess I think it's like issues like this if you're not considering how like let's say you have 3 classes. Oh yeah, this is the kind of and then you have these 2 small classes, right? You take these 2 small ones and you make it no, this is the counter example. Like, you take this all. If you have a class that goes from like 7 to 10, and then from noon to 5, you know, the class that literally just runs. Once you like, you go on like another because you select the actual class. There's no bio actual class. But if you go, I don't know, like, is there any other, specific, like, I was originally thinking you need well, yeah, I was like, that's not really my thought. Like, let's say you're yeah, so we like you're from 4 classes. Let's say one of them and then one is
Oh, you're seeing like the left one.
I think that would work. Because you'll never overlap.
I think there's.
I actually can't right? Because
Try every possibility.
you can say you're trying to say you're
You can do it in
all the ones that oh yeah, I guess that doesn't work. Yeah, because if you think this one is like 9, taking up to 6 even if you
Oh yeah. Like if it's like well, like think about it like this. Or like you're having like here, right? This is the one that starts with the second, right? Sorry. We are looking at UMass, like just like which one can we, if we want to work right, which one can we choose? So, I just look at that example, which one do we choose that gives us like the most oh, I agree with you, I just like yeah, like in this case, yes, like it's the bottom, it's the person who matters.
oh, sweet. We have by what end? We sort by end.
They didn't like want like exclusively.
I thought that too, but I don't know.
What I was thinking was, let's take let's say we have some other strategy. So you get like a right? We want to say that gets at least as many classes. So what we could say is, well, we can put them in order, right? Let's say you have some solution, not some solution. Let's say you have some assignment classes. Right? You put them in order from left to right. So the first one is right. I think that's what I'll do.
All right. So I'm going to talk about 4 different heuristics that might be the right answer for you all to consider. So I'm just going to say them first, and then I want everyone to consider them, and then we're going to discuss which one is right. The other 3 are going to be, in fact, wrong. Okay. First up, 1. Repeatedly choose the shortest class. Choose the shortest class. Repeatedly. 2. Choose the earliest class repeatedly. 3. Choose the class that ends the earliest. So instead of earliest start, it's earliest end. I'll call this start so that it's more clear. And 4, choose the class with the fewest overlaps. Honestly, I appreciate the dramatic moves. Gives me time to write. Okay. I want everyone to think about all of these. 1 of these correct, 3 of them are wrong. Going to give you a minute to digest. And we're going to go through and see what people think. Okay? So mentally choose. Don't switch your answer based on what other people think. It's perfectly fine to get this wrong. It's your first time seeing a problem like this. It's fine. Okay. Everyone locked in? Everyone know which one they have? Presumably most of you came up with one of these 4. They're the most common ones to come up with. All right, let's go through in order. I'm not going to point out which one's right as I go, by the way. I'll say it after. Who chose number 1? Okay. Who chose number 2? Cool, cool. Who chose number 3? Okay, slightly more. And who chose number 4? Chose number 4. Okay. Well, let's start with the last picked ones. So, shortest class. This is not the right answer. Can anyone give me any idea as to why? Sure.
You could have a class from like the start of the day, 10-minute class that overlaps them both, and then
So 2 is definitely possible. Shortest class here. Neither of these would be viable options after that. Cool. Correct. So this is a counterexample. We're going to be doing counterexamples for each of them, but then the one that we have to prove correct is going to be a little bit more involved to prove. Not very, but a little bit more. Earliest start. Sure.
Let's say you have a 5-hour long class and starting at 7:10, there are
Exactly. By the way, this first one is going to, I believe it has it's off by an order of 2 at worst. This one is off by infinity at worst. So there are actually better wrong guesses, by the way, just so you know. But not to call out anyone who put that, but that one will end up having worse analysis. Cool. Now, for 3 and 4, one of those is correct, one of those is wrong. Does anyone want to give me a counterexample for one of them? Either I'm choosing the earliest end of the classes, or I'm choosing a class with the fewest overlaps repeatedly. Yeah.
Would 3 be very similar to choosing a class?
Which one?
Number 3.
Number 3 be starting the latest. So you're saying, well, it wouldn't be starting the latest necessarily. It's just ending. So they aren't equivalent, if that's what you're saying.
Yeah. Say like, oh, 3 is a very similar algorithm to like a class that starts the latest. That like.
I mean, there are definitely similarities. I'm particularly looking just for a counterexample right now, though.
Yeah.
But that is an insight. Do you have any counterexample for either one of them? How about this? Now that we've ruled out a couple of them, I want to see all the hands this time, by the way. Who thinks that it's 3? And who thinks that it's 4? Okay. I'm gonna give you all a minute or so to come up with a counterexample for the one that you think is wrong. Okay?
Really? I was really good at that. I'm so bad at finally on the final, they actually made a question about like finding eigenvalues. It's so complicated. So like on the final answer, we like they realized that they have to be oh, yeah, because it was and for the C4.
Necessarily means like the first one.
All right. All right. So, anyone want to volunteer a counterexample to 3? A little bit. Anyone? That makes sense, since it is the right one. How about 4? Anyone got a counterexample for 4 they want to share? Sure. Yeah. I know yours. I'll just do yours. She just shared it with me a second ago. This is her counterexample. I'll show you another counterexample, which is the one that I came up with. But here is hers. Just this and a bunch of classes. So this one will have the most overlaps out of these. We can even, I guess this is fine. We can do it like this. Yeah, this will have the most, or I can even just do it like here. I'll come up with a different one. This is fine though because this one will have the fewest. No, this one has 5 overlaps then. Sorry, I'm gonna give my counterexample.
Basically, the first slot, like the first.
Well, if you fill in these with a lot, then no, it doesn't work either.
No, the first class would be the smallest one.
Yeah.
All the others would be bigger but equidistant, like equal.
Yeah, but if I put any here, then they overlap with all the rest of them.
But then progressively they would overlap with less. They
Let me give the other counterexample rather than this. Sorry. The other counterexample I'm going to give, much simpler by the way, is just going to be this. So you recall this? Cool. Double these up. Or actually, no, I can do like a little bit less than that. Yeah, like that. So both of these are going to be. Oh no, I need to make them overlap with all of that.
Just add more lines below. Just add
Yeah,
a ton
yeah,
of lines
just
below.
add a ton of them. There you go. I make them all the same or no, I can't. But sure, it does. This counterexample does work. I'm pretty sure. There is a counterexample for it. I promise. Sorry. No, this I think doesn't actually work.
No, because if you try to choose the one with the least overlap, you get the one in the middle, which is like.
No, because if I make these all the same length, if they overlap with it, then it counts as an overlap for this one and for that one. Exactly. Okay, there is, I promise, a counterexample for this one. I thought this one was, and I was wrong. Okay. Sorry. There is a counterexample for it though. If you like, okay. I will come up with one later, and I will share it with the class. Okay. How about that? There, I get some homework now to post on Piazza. Fine. Yeah.
I mean, I heard someone ask this, but like, how is it
For what?
for class with the same overlap?
So you have some sort of tiebreaker. A reasonable tiebreaker would be this one, except the algorithm's wrong still. Yeah. Anyway. Sorry about that. Yeah. I didn't actually write down a counterexample because I thought that one was right. Sorry about that. Yeah. No, but the correct answer is this one. Regardless, even if this one was correct, it requires other like computation, so it would be slower regardless. So this would be a better one. But this one is not correct. By the way, it is not correct. But if we do this, why does this work? Does anyone have any argument? Like any just verbal argument first, and then we'll talk about formal proofs. Sure.
We're saying that choosing the earliest like during the class that we selected and
It's okay. We could get to there with a contradiction, but I think you have a little bit of gobbledygook in the middle that actually makes it not a full line of logic. But you're getting at the heart of the idea. This would be like a conclusion that you could draw from an argument. Anyone else want to give an outline of an argument here? Yeah. Yeah.
If you pick the earliest end time.
Okay. That's okay. This is our first time doing these. Yeah, sure. In the back. Okay, so I think yours is closer to a fully fledged arguments case, but a little bit of gobbledygook too, just a little bit. But you are more or less on the same line. I do want to clean it up a little bit. Is that?
I don't know.
I know, I'm sorry, I'm pointing at him.
S&T set.
Just make it a lemma and then it's true because the lemma's true. That's what you're saying. Alright, okay, so back off. Okay, Tony, you want to get for it?
Yeah, you can say like the earliest ending class can never have a shorter class within it.
Okay.
So what that would mean is that if you take the earliest ending class, then there's no set of smaller length classes within it because those classes would end earlier.
Okay, another good insight, not a full argument, but a good insight. Would you like to give it a go?
And then that gives us more for our next class to pick. And if we keep doing that over and over again, our solution will have the maximum amount of end of threes possible.
Okay, yeah. So this is an exchange argument, which we're going to talk about in a second. This is the second proving technique. The first proving technique is actually very clean for this one, so I'm going to explain that one first, and then I'm going to explain this one. That's a perfectly good explanation, though. So first explanation here is, let's imagine that we have our full time scale, right? We're going from 0 to t, I'm choosing that without loss of generality. It doesn't matter if they're different numbers. Then we imagine if the earliest class we choose is our, so we can think of choosing them from the beginning to the end, rather than choosing them arbitrarily. Let's think about that, right? So if we choose it from the beginning, right, the earliest class that we're choosing, if it ends the earliest possible, so let's say there's a bunch of different options, like all of these, we choose the one that ends the earliest, right? Then we're going to fill in this time, and now we have all of this remainder. I'll call this like lowercase t. Maybe I'll call it t1, lowercase t1. So now the remaining time that we have is from that start to this end. If I chose any of these other ones, then I would have less options. So this is a greedy stays ahead argument because no matter which one of these I choose, I'm adding one class to my total, right? The number of classes that I have, but I'm only removing further options if I don't choose the earliest end time. So if I have some class that starts anytime in here, that's no longer an option. So the basic idea of this is that by choosing the earliest start, I leave myself the most flexibility. So none of the options that I would have by choosing any of the other things are removed by this option, and it's possible that some other options are allowed only because I chose the earliest. Yes?
Just say it's like you chose the earliest.
So it's not going to be the, it's not the earliest shortest class, it's the earliest ending class, right? And the idea is that by choosing that one, rather than choosing any of the other ones, then I know that I'm leaving as much as possible. This is very, like, you can sort of see the connection to the exchange argument here, where if I were to exchange this with any of these other options, I would only have less flexibility. I would only have fewer possibilities of what I can do with the rest. Any of those other options are still allowed by this option, though. Does that make sense?
Yeah.
Okay. So, so that is a greedy stays ahead argument for this. Does anyone have questions on this, by the way? Hopefully this proof is very intuitive. Yeah.
Could you just explain it again?
Sure. Okay, cool. Running it back. So the idea of it, the core idea, is we have some amount of time, right? And that has some amount of different options, right? I have different options for how I could choose my classes. And we're saying if I look at the one that is at the beginning, right, for each one of these, right, then if I choose the one that ends the earliest, then I will remain with all of the options to fill all of this area. So like there could be a whole bunch of different classes that could fill this, however I want to. In here, right, there's a whole bunch of different classes, and I'm allowed all of them if I have as much space left as possible. But if I were to choose any of these other ones, I would lose some of the options. So because, if I were to basically consider this now a sub-problem, if I remove this from the beginning and then consider it a sub-problem, I'm allowed, the amount of classes I can fit in this larger space will necessarily be higher. Does that make sense? Okay. That makes sense to you? No round three? Okay. Yeah, so that's the core of the argument. This problem happens to be pretty easy to prove by greedy stays ahead. If we're being a little bit more formal about this, we need to, say that I will have this much space, and I'll have greater than or equal to the number of classes that can fit in this space as could fit in this space. It's just it's an intuitive fact. We don't really need to prove that super formally. Okay, is everyone comfortable with this? This proof should hopefully be pretty intuitive. The other proof, the other way of doing this, the exchange argument, is probably going to be a little bit less intuitive, but is a good technique for problems where you can't come up with something like this. Okay? So the other technique is the one that is somewhat contradictory. So again, this is basically induction. you can see that. It's sort of, you show greater than rather than this, but you induce on the number of choices you make, and then you show that we are going to continually stay maximum. The other option is essentially a contradiction. So the contradiction works like so. We're going to have our assignment. So we'll call ours alg, right? So we'll have some assignment of classes we'll call alg. Let's say it's something like this, whatever it is. And then we'll also consider some arbitrary optimal solution. So we're going to arbitrarily define some optimal solution. When I draw them out, it's going to be obvious that it's not optimal, but I need to make it not optimal for this argument. But I can do something like this, this. Let's say that's the optimal. But I'm defining it as some arbitrary optimal decision. And now what we can do is we can go through this, and we can iteratively exchange decisions. So I can say, okay, originally I chose this long one. Right, I want to turn optimal into algorithm, right? Into our algorithm. So this is like ours, and this is the optimal given by the grace of God or whatever. Okay? We're going to take this, and we're going to exchange it with this one. And what we're going to see is that by doing this, right? So exchange that first one for the second one, and we'll see that we have more time. We have more flexibility, and then we can iteratively do this. We can now exchange them repeatedly. I exchange this one with this one. I exchange this one with this one. And what we show by doing this argument, if we repeatedly do this, we see that every single time we do this, we will have the remainder be once I swap these two, the number of classes I fit will be the same or greater, right? And as I swap the next one, it will be the same or greater. And repeatedly as I do this, then it will end up being the same or greater, meaning if I have the same or greater number of classes in my algorithm as I do in the optimal, which is the maximum by definition, then algorithm must be optimal. Does that make sense? So if I show that algorithm's decision is as good as optimal, then it must be optimal. Okay? Maybe slightly heavy on the verbiage at the end there, but if anyone has any questions, ask now. Yeah.
So basically you provide an optimal solution and then you compare it to the algorithm or switching it.
Yeah, so we say I choose some optimal solution, some arbitrary one that's given to me, and I show that by swapping it, repeatedly exchanging choices from the optimal solution and the algorithm solution, that as I do that, I repeatedly am keeping my algorithm as good or making it better. Keeping opt as good or making it better by doing this exchange.
Why are we doing
So I mean, in this case, they have the exact same number. But let's say that they have the exact same number, right? I mean, okay. This is a theoretical thing, by the way. I'm not saying here is your solution, here's the optimal solution, count them. Optimal is like an arbitrary thing, right? So I'm saying I have some arbitrary decision made by optimal. I'm drawing it on the board, and I'm giving it a specific optimum just to make it make sense. But we're going to say that we're giving it arbitrarily, right? We're going to say that it's some arbitrary optimum, and it can even be the same as the output of our algorithm, but then when we do the exchange, there's nothing to exchange, therefore it's fine. Yeah, so the exchange argument is basically just the idea of if we take our optimal solution and slowly transform it step by step into our algorithm, it is better or the same. And if it's better or the same, then it's better than optimal. Then it is optimal. Yeah, and I've drawn it here where we're starting from the left and we're iteratively replacing them one by one from left to right. This will make sense for this algorithm in particular, since that's how we're defining the algorithm, but it's not necessarily how we need to do it. I could start from the end and do the same process, and it would show that we can increase it, but it'd be a little bit trickier to prove. But doing it this way is not necessary. We can do it arbitrarily. I can pick a random class and swap them and repeatedly do that and show that it will improve the result. Cool? So these are the two main methods that we'll have to approach greedy problems. I very well might give you a greedy problem on the exam. They're generally easier, but it's good to know how to approach them. Speaking of which, SI, Tomas, is going to be doing a greedy coverage tomorrow in the SI session. He has props, and it sounds like it's going to be pretty fun.
This is something I've been thinking about, like, what I'm going to do when we do greedy algorithms for a while. We're going to be playing cards. It's going to be like a very simplified version of a Spanish card game. And there's a strategy that you can find that will always win, and it's a greedy algorithm. It's not like as obvious as this, maybe. But yeah, point is, we'll prove that it works with an argument like this. It'll be fun.
Yeah, I think, so greedy is a topic that I am not super inclined to spend much class time on. This sounds like a very fun way to get some exposure to it, though. So I'd recommend it. Yeah, go put it on the board. Okay, yeah, so as a little recap here, the main two ways that we're going to approach greedy algorithms, the intuitive names are greedy stays ahead and exchange, and they are in secret induction and contradiction still. Yeah. We can't just write the word exchange and then put done. So what it will do to name it exchange is that it will prime the reader to know what you're trying to do. Really what that would give you is a little bit of partial credit in this class, and in real life that would give you some, I guess, benefit of the doubt. Right? It would prime readers to be able to read it. I mean, it's really not important if you use the specific name in terms of correctness. But it makes it a little bit easier to understand sometimes, so it's okay. It's perfectly fine. You see that I kind of avoided using their names, even though they're intuitive and they're kind of nice to remember, just because they aren't important. It's not an important part of the whole thing. It'll just help you remember them. Greedy stays ahead, I remember from taking 311, so clearly it stuck around in my head. Okay, so I think it really sucks that there's no clock. Okay, that's just about time, but. Before we go, I just want to briefly mention this and one more administrative thing. So Huffman encoding, I didn't really plan to get to it today, but I wanted to put it on the board. This is another greedy algorithm that is a bit more interesting in terms of its application. It's for data encoding. It's a pretty interesting thing. It turns out we can sort of dynamically choose the bit length of our encodings for different characters, if that is an interesting sentence to you, or if you want more practice with greedy, you should look into that. And in particular, I just uploaded onto Piazza the entirety of the slides from a different version of 311, so you can look through all of them, and there are slides covering Huffman encoding. So if you'd like to look at it, it is a good way for you to practice greedy, or any of the other topics in class. You can also see how the order of how I've done the class is basically reversed from the other version. Okay, with that, you are free to go. Goodbye. Yes.
Would you mind explaining the exchange part? That didn't make sense.
Okay, I'll answer the other question first, but I can explain after that. Which is what?
Between 4 and 1, which is like better?
I think 4 is slightly better, because this is an approximation ratio of 2. I don't know this one off the top of my head, but I guess it's better. That would be my guess. Why, did you make a bet with someone? Or?
No, I like specifically went for the first one.
Yeah, it's an intuitive answer, but yeah, no, it has a factor of 2 at least off. I'm pretty sure it's 2. Yeah. Yeah, no problem.
Do you remember the first dynamic problem you gave me?
Yeah. Was it rod cutting?
The chicken wing.
Yeah. That's knapsack.
Yeah. Can you give that problem